we're going to do a problem about least upper bounds. So far we have learned that if you have an increasing sequence and you can prove that it has an upper bound, then the theorem says there's a least upper bound. Now let's look at this particular problem. We have a sequence where x1 is square root of c is some constant, x2 is the square root of c plus x1, and you keep doing that. Then xn plus 1 is square root of c plus xn. So after a while, you have a whole bunch of square roots stacked up. So the problem can appear to be very confusing, but it's actually come out quite straightforward. So here's what we're trying to do. First, we show that it's an increasing sequence. That is, xn is less than xn plus 1 for all n. Next, we show that it's a bounded sequence. That is, xn is less than some constant, 1 plus square root of c. And then once we show that, we know the limit exists. Then we will calculate exactly what the limit is. So, step 1. Step 1, we have to show that it's an increasing sequence, and we do so by good old mathematical induction. So to do mathematical induction, you have to first show the first step. So x1 is square root of c. You do 1 and 2. x2 is equal to, pardon me, why did I say square root of 2? Square root of c. There. x1 is the square root of c. x2 is the square root of c, is c plus square root of c, which is, well, if a c plus something is bigger than just c itself, so this is definitely bigger than x1. So that's good. And then next we do the assumption. Now assume that we do the assumption that says assume that xn is bigger than xn minus 1. Okay, from this assumption, we have to prove the next step, which is xn plus 1 is bigger than xn. So you prove it, then that will complete the induction process. So to do so, you add c to both sides, bigger than c plus xn minus 1. Then take the square root of both sides. The equation still holds. Okay, and then what is c plus xn? It's just xn plus 1 by definition. See, right here, this is exactly what it is. And then similarly, this thing is just xn. So your induction is done. A quick, clean 3-step proof. And we already finished part 1. Next, let's do part 2. To show that the sequence is bounded by a fixed number, we assume that it is not, okay? And then prove a contradiction. So suppose that it is not bounded, so that xn plus 1 is bigger than this 1 plus square root of c. That's what we're trying to prove, is this thing. So, but suppose it's not true, okay? Suppose it's bigger, or bigger than or equal to something like that. Then, or maybe we should say bigger than or equal to complete the logic. But anyway, it doesn't really make any difference. The proof goes the same way. Now, if you suppose that, then you define it as this thing by definition is square root of c plus xn, which is bigger than 1 plus square root of c. You square both sides, which gives you c plus xn. I'm just doing algebra here. Is equal to this thing squared, which is c plus 2 square root of c plus 1 squared. And then you clear that out, so you get xn then is bigger than, get rid of the c's, you have 2 square root of c plus 1. What is that? Well, that is definitely bigger than just 1 square root of c plus 1. Okay, and well, so then we have this particular condition. That is, if xn plus 1 is bigger than this number, so is xn. In other words, the backward thing is deducing. Each one going back will be bigger than 1 plus square root of c, which will eventually imply, okay, this implies that x1 is bigger than or equal to 1 plus square root of c. But, however, but what is x1? But x1 equals to only square root of c, and this is definitely no bigger than 1 plus whatever it is. So then we arrive at a contradiction. So then we have part 2 proved. And in the next video, we will do part 3. I'm out of board space here.